Thank you very much for inviting me to talk about planetary heat flow. Of course, we would be, very privileged if we had at least a few percent of the data that you guys have. We're not talking about hundreds, thousands of data points. At the moment, we have, as I will show you, basically 2 planets from which we have, an indication or measurement of heat flow. What you see here in this picture is actually a selfie that our InSight lander took of itself a few days after, or sols, as we say in planetary science, after landing. What you see here, that chimney, that belongs to the heat flow experiment. And on the right-hand side here, you see the heat flow experiment deployed, and then the penetrator going into depths and carrying behind it a chain of temperature measurements. That was the idea how we would actually want to do it. But before I speak about that, I will introduce a little bit about the heat flow measurements on the moon that were done with the Apollo missions and of Io, the satellite of Jupiter, where we have very high heat flow values and quite reliable remote sensing heat flow. Now, I don't think I have to motivate heat flow measurements to this community, but let me just say the way I understand it is basically the heat that the planetary engine dissipates, that can be used to characterize the engine itself and the work it can actually do, although we don't really know how the efficiency of that engine actually is. It's a pretty difficult problem. But anyway, we're getting tectonics and we're getting magnetic field from that. And what you see here is a calculation of plumes in the interior of Mars that Ina Blaser has calculated that can explain the surface volcanology on Mars, and also the magnetic stripes, because Mars in its early evolution had a dynamo, as we now know today. What you can also use it for is constraining the composition of the planet. And here we show a calculation. Oops, that was not what I wanted to do. Oop, where am I? Okay. Here it is. Okay. What I show here is a map of the thorium composition and potassium composition of the Martian mantle, and calculated heat flow values in comparison with predictions of various chemical models. And as you can see, these are the heat flow contours that you can actually discern or decide between these models should you have the heat flow measured. What's also shown here is the URI ratio. That is the ratio of the contribution of internal radiogenic heating to the heat flow. And you can also use that to concentrate that value, which is something that geodynamicists are very much interested in. No, this is the wrong direction again. Okay, now talk about the lunar surface heat flow. The lunar surface heat flow was measured during the Apollo mission, and it remains the only successful in situ surface heat flow measurement to date, unfortunately. We haven't been very successful in trying to repeat that. It's in the 60s, and now we're here in 2025. Now, of course, when you plan a heat flow measurement, you have some idea how large would actually that heat flow be. What you do for that is you would do basically a mass scaling. So you take the mass of the moon, you think that the heat flow is proportional to the mass of the planet. And if you do that, you get at roughly 20 milliwatts per meter squared. So that's the value that you start with. But then you need to avoid, as I don't have to tell you, the perturbations of the insulation. And you can see that you have to drill, to some multiple of the thermal skin depths. And for the moon and for Mars, we're actually quite fortunate in comparison with the Earth that the thermal conductivity of the regolith, or the soil of these bodies, is very low. We're talking about something like 10 to the minus 2 watt per meter Kelvin, which means that the thermal skin depth for the diurnal wave, for instance, is only 2 centimeters. And for the annual wave on the moon, it's only 30 centimeters. And then there is a precession of the lunar axis that adds another disturbing factor that has a precession, that has a thermal skin depth of a little more than a meter. So actually the conclusion is that on the moon, it suffices to go something like a meter or 3 meters into depth to do a reasonable measurement. But on the other hand, this also helps you with a thermal gradient, because if the thermal conductivity is low, then of course for a given heat flow, the temperature difference is relatively high. So that's also better than on Earth. But what we need to do is we can't take drills and take them to the lab to measure the thermal conductivity. We have to do that in situ. That's another complication. This has been done on the moon with that instrument. So they had 2 bridges where they could measure the temperature and the temperature gradient for about a meter, and then a few more thermocouples as you go to the surface. The holes, where these sensors were put in, were drilled by the astronauts with a rotary percussion drill. And here is a cartoon of what's been done during Apollo 15, where they actually didn't reach the target depths. They reached a little more than a meter here and a little more than 1.5 meters over there. But still, I mean, that was sufficient to do a reasonable estimate. And what you see here on that side is the David Scott handling the sensors here and the bore stem. And on that side, Apollo 17, where they actually reached the target depth, here is a deployed instrument, and there is here is the electronic box. When you talked about the perturbations in the first half of this, I mean, this was a problem at Apollo, because the astronauts jumping across the surface and doing this and doing that, they actually perturbed, the situation quite a bit. And those, with that thermal conductivity or thermal diffusivity, it takes tens of years before that goes away. So that was a problem for the interpretation. They did record the temperatures years after the mission saw that the temperature changed, but then at some time, the Apollo instruments had been switched off because of funding reasons, actually. Now, another problem with the heat flow measurements, there were actually 4 were planned. Where are we? Over here. 14, 15, 17, 16. That was actually 13, which blew up after launch, but that was replaced by 14, but these didn't work. So 15 and 17 worked. Now, what you see here is a region that we only came to know later. It's the Procellarum Crete terrain, an anomaly in thorium concentration on the moon. Nobody really understands where this comes from geologically, but it is there. These 2 measurements were a bit unfortunately, located for that. He would have wanted to measure here, and he would have wanted to measure over there. This is actually the point where Lister this spring tried to measure the heat flow. This is much more into the region that, from thorium-wise, at least, is more characteristic of the moon. But these were the 2 measurements. They were 21 milliwatt per meter squared and 60 milliwatt per meter squared. So people have tried, to get an average value, predict an average value for that. That would be characteristic of the moon. And this is the 12 milliwatt per meter squared that are listed over there. So we would like to have a measurement, of the heat flow of the moon, somewhere away from this PKT region here, and one right on the middle. So Apollo 14 would have been perfect, but that unfortunately didn't work out. Attempts since Apollo, the most recent attempt was this spring, where the Blue Ghost mission, commercial mission actually, the first commercial, it's not actually the first commercial mission, one of the first, was trying to measure using the heat flow probe Lister that had a pneumatic drill. So they pumped helium gas into a borehole and blowing the dust out. That worked only for 90 centimeters, and then quarter crane stuff accumulated at the bottom, which then frustrated the further penetration. And unfortunately, the data, both the depth reached and the data that they were getting were insufficient for a reasonable heat flow measurement. But they'll try again next year on another commercial mission, Draper Apex, and they'll be using more energy for the pneumatic drill, and maybe they get deeper and get a better measurement. Another attempt that people are using is to measure the surface temperature in permanently shaded craters. And that has been done, for instance, by the group Wyatt here, published 2 years ago. But the value that they got was actually probably unrealistically low, of about 5 milliwatt per meter square for the heat flow on the poles. Now, it is questionable whether you can actually do that on the moon, but you can do that at Io. And we're now in the outer solar system, in the orbit of Jupiter, where we have the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. And the 3 inner moons form the Laplacian resonance, which causes tidal dissipation, together with the big mass of Jupiter, of course, of Io, which results in a tremendous heat flow. Here is a map of the temperatures of some of the volcanic features of Io. This is a map derived by Galileo, and this is from the Voyager missions. And here you see a gigantic plume of eruption of Pele, and here you see a lava lake, Loki, and then there are others like Kung, or this guy here and over there, that are volcanic flows that are pretty high in temperature. So the temperature varies between 90 and 115 degrees Kelvin. And that can be converted into a heat flow map. And you see that Loki here, for instance, has a heat flow of 20 watt per meter squared. And the average value is 2.6 watt per meter squared. So 100 times more than the moon, although this is a body of the size of the moon. So you would expect 20 milliwatts per meter squared, but not 3 watt per meter squared. But that can be explained by tidal dissipation. So this thing is permanently forced by the tides raised by Jupiter, and it's burning its volatiles. At the moment, it is burning sulfur, which is extracted through the surface momentarily. Now, going then to Mars. This is our InSight lander after the deployment of our heat flow probe, on Mars, we know now, and the estimates also indicated that the skin depths are a few times the skin depths of the moon, because the Martian regolith is different from the lunar regolith. It's not as fine-grained as the lunar regolith is. Therefore, we targeted for a depth of 3 to 5 meters using an instrument. And also, I should say that we can use time here. So if we're measuring for about a year or so, we can then compensate for a loss in depth that we may encounter when we're as we burn the surface. Also, let me say that the calculations or predictions of the Martian heat flow were ranging between around 35 milliwatts per meter squared, but later we have tried to invert seismic data to arrive at an estimate, and that was on the order of a few around 20 milliwatts per meter squared. So that's a model calculation. This is from seismic data, and this is also from seismic data. And the Martian heat flow, we believe, reflects the crustal thickness. So it's basically such that the Martian crust is enriched in radiogenic elements, and we would expect that the heat flow would be basically reflecting the thickness of the crust variations, which we have a good idea of from gravity data. So here was the location of the InSight measurement. Now, here is the instrument. So you see that is the penetrator. It's a mechanical diode that directs momentum forward and compensates the recoil with a coil spring down here and through friction on the hull of the mole, which is important. And then we have the temperatures imprinted on this tether here, and we use heater foils in the ball of the penetrator to measure the thermal conductivity. So we go down 50 centimeters wide, take a measurement of thermal conductivity, and go another 50 centimeters, and so forth and so forth. And then when we're finally down there, we measure the thermal gradient using these temperature sensors imprinted on the tether. Now that was the plan. Now there is, we knew that at the beginning there was a critical phase of the deployment. So here you go down and you compensate part of the recoil by friction springs. And when you're in the ground, you have overburden and hull friction that compensates the recoil. But there is a transition, where you are just inserted and you need the friction by the sand around you to compensate the recoil. But unfortunately, there was no sand. There was what we call a duricrust. And the duricrust looks something like this here. You can see here, these are balls and not sand as you would expect to flow and rest against the hull. And that duricrust basically took away a third or so of the friction that we actually needed. And that caused, basically the penetration to be unsuccessful. And now we tried to compensate the lacking friction from the duricrust by placing the arm of or the shovel on the back of the arm against it and provided friction. But then when we tried to penetrate, and we penetrated, then we tried to penetrate further, the mole came out again. And then we took it again, and then we finally managed to put it about a few centimeters below the ground. But then we basically had to give up that experiment. So we could only use the mole then as a thermal probe, which we did then, and we used it to measure the thermal conductivity. We also used it to measure the temperature as a function of time over a year, and over there, and the diurnal period to measure, to estimate the thermal diffusivity from that. And then in the end, we used both the penetration profile, also the signal that was generated by the hammering that was recorded with the seismometer to measure the elastic properties, and then we determined the thermal diffusivity and the thermal conductivity, penetration resistance, and the density. And what we learned basically is this from the New Yorker, that there's nothing as complicated as sand. And with that, thank you very much. And,